Okay. Hello and welcome to this week's Introduction to Structured Programming. We are in week 8 and today we are talking the second time about memory. So last time we've seen the heap, malloc, calloc and free. And today we will talk again about the heap, some additional functions, how we can use the heap, and also some fun stuff, I think, because we will do things that you shouldn't do. So you shouldn't do it in the assignments, but we want to break something today. But as always, let's start with some organizational stuff. We are in week 8, so today again the weekly exercises will be released after the lecture at 7 p.m. and these are the last exercises already for assignment 3. So assignment 3 contains the exercises for week 7, last week, and this week, week 8. And next week there is a break in the lecture. There's only the practicals. And we will continue on the 4th of December, so in 2 weeks with, are there only 2 more lectures left? Wow, okay. And then we have one Christmas special, but there are 2 more regular lectures left after today. Wow, okay. That has gone fast. So as always, the deadline for the exercises is the assignment deadline. They belong to assignment 3, so the deadline is the 10th of December. And as always, a reminder, if you do not pass more than 50%, you will get the 25% deduction. But I think there are 5 exercises, so you have to pass 3 of them. That's manageable.
Definitely.
Okay, start with a recap as always. Put out your phones. We have 3 questions for you. The first one, let's start with an hopefully easy one. In which situations is it better to use the heap?
Yeah, so do we need the heap if we only want to read one keystroke? So just one key that the user has entered. Do we need the heap if we want to read an arbitrary long user input? So it can be any number, how long the input could be. Do we need the heap if we want to store the points of the exam of 20 students? I mean, depends on how many points can be achieved, but yeah. Or do we need the heap if we want to store and swap 2 values? Again, some discussions.
Yeah,
so
interesting.
Let's see if it's that easy.
Okay, last few seconds for you. Okay, let's see what you said. Yeah, okay, so the most obvious one is we want to read an arbitrary long user input because that's the classical use case for the heap. Because at compile time, we don't know how long this user input should be or could be. And then we use the heap because we can allocate memory on runtime when the user actually opens and works with the program. The other thing, there might be a discussion about store the points of the exams of 20 students, but the key point here is we know that there are 20 students, so we have a fixed size of students, so we can also use a local array on the stack or whatever, because there's a fixed size. And whenever I have a fixed size, I can also use the stack, for example. When I store and swap two values, I can, of course, and we have also seen it in the swap example, use just local variables for that. I could use pointers, of course, when I swap two values, but I don't necessarily need the heap. And read one keystroke, I could also, of course, store that one keystroke into a local variable. I don't need the heap for that. Okay, next question. A bit more advanced. What is the correct way to allocate memory on the heap for 5 floats and initialize them with 0?
Yeah, for those who did the weekly exercises already, they might have an advantage here, because at one exercise you should have used calloc, so maybe you know the difference between malloc and calloc.
And there is only one right solution
Correct.
here.
Yep.
Okay, last few seconds. Let's see. Yeah, okay, great.
Wow.
So this is the correct one, float pointer nums. And we call calloc because calloc initialize all our memory with 0. And calloc has this special notation that it takes 2 parameters. So the first one is the number of elements. The second one is the size of one element. So we want 5 times the size of a float, so 5 floats. Malloc has a different notation, just one argument, the overall number of bytes. But in this case, we wanted them to initialize with 0, so only this calloc works. Okay, last question for the recap. A tricky one. In which segment is the variable my name stored?
Yeah, that's really a tricky one. That's not that easy.
Okay, last few seconds. Let's see what you voted for. Yeah, I thought it's like that. So many of you say it's the heap. I think it will change. Yeah, great. So actually it is the stack. But why is it the stack? So we are allocating memory on the heap. Why is it not the heap? Why is it not the data segment? So let's talk about the data segment first. The data segment, we have seen that if I create a char pointer, it's stored on the data segment. Yes, the string is stored on the data segment. The variable which points to the string is stored on the stack. That's a difference. And the same applies for the heap. I can allocate memory on the heap. So I get memory from malloc back, which is on the heap, but I store the address that points to that memory on the stack. Very important. So stack is here correct because my pointer, which just contains an address, is on the stack, and the pointer points to the heap. That's why my name is stored on the stack. Actually, I think I cannot use the heap without the stack. I always need the stack because I always need to store my addresses on the heap somewhere to can access them. Okay, any questions to this? Yes. The question is, where is this null stored? Actually, null is just another version to say 0, yeah? And this is like the memory location null. So you can store like any other address, yeah? And null is just a different, yeah, an acronym for saying it's the address 0. And we will see in the next few slides why that might be helpful. It is actually very, very helpful to have this null because we are talking now about segmentation faults, and you have seen a segmentation fault in the practicals before, but I think we will go one step further and also try to produce the segmentation faults on our own, and we will also see what is doable, maybe more than we think. So what is a segmentation fault? Let's see about the theory behind. A segmentation fault is a program, or let's say a piece of program, that attempts to access memory locations that do not belong to the program. So we are doing a mistake. We are accessing something that does not belong to the program. So when I create this int pointer here and initialize it with null, what happens is this is actually just a pointer to the lowest possible address, which is null, 0, the 0 address. And the 0 address is never accessible for me. So the lowest addresses I can have in my program are in my code segment, so my source code itself. They are at 0x5, whatever, yeah. So quite high already. And I try to visualize it because I have some space here for very, very low memory addresses. And as soon as I access them here, I will always get a segmentation fault. So this initialization here works. This is okay. But as soon as I want to dereference this pointer, and so I say I want to access the address 0 and write 1 there. So I want to write somewhere which is obviously not in my stack, not in my heap, not data segment, and not code segment. This produces a segmentation fault because we are accessing a memory location that does not belong to our program. And this is the cool thing with null. When we set something to null, like here, or also as you have seen in the practicals today, we can guarantee in a way that as soon as we want to access this or dereference and access this address, our program will stop immediately and we see that there's a problem, we see the segmentation fault. And as Michi said today, sometimes it's better to have a segmentation fault so we know that there's a problem. In contrast, if I don't get a segmentation fault and the program still runs and runs and runs, I will maybe never see that there is a problem at all. So what I now want to demonstrate you is that I want to access areas on the stack and on the heap that do not belong to me. So I have here, yeah, that works, okay. Let's say I created a variable, local variable, so we are on the stack here. And what I want to do is create another variable with the address of my variable. So we know that this is my local variable with 0, and this is just the address of this variable. What I can do now, of course, is printing the value out of memory, dereference that, and what will be the output if I compile that. I hope you see it. Okay, I get a warning. Why did I get a warning?
I think there's a missing.
Yeah. Okay. What will be the output? 0. Hopefully. Yeah. Okay, this is the 0 here. Let's make here a new line. It's a bit easier to read. Yeah. Okay. Now I get the output 0. So that works. What if I say now, okay, I don't want to have the address of my variable var, but I want to have the address of my variable var plus 10. So I'm 10 times away from my variable, and I want to see what's stored there, because this is my address of my variable. I add 10 to the address, which is then 10 bytes away from my address, and I dereference that and see what's stored there. Let's see what's stored there. I have no idea what's stored there. It might be null, it might be something else. Okay, this value is stored there.
Wow.
So we are now at, I don't know, any other memory location, and we can see what's stored there. Let's say we want to have 100 times away. There is this value, okay? But still no segmentation fault.
That's
so
interesting.
We are accessing a variable or a memory location that is 100 bytes away from our original variable, and it still works. Interesting. Let me try to increase that to 1000. It still works. There's 0. Let me try to increase that to 10,000. Ah, okay. Now I get my segmentation fault. So I can actually access addresses which are very, very far away from my original ones, and it still works. So a segmentation fault does not mean you are just one of your variable. It says you are way too much away from what you have or where you should be, because I'm now 10,000 bytes away from where I should be. That's large. Let me also remove that, and let's see how the heap reacts. So I create something on the heap with malloc. Let's say 3 bytes size of integer. Okay, yeah, check for null, but what I want to do here now is I have now my heap array with 3 integers. What happens if I say I want to store something at the position 5, which is obviously off? So I'm way too far of my array. Let me just compile that once again. Let's see. Okay, it works, and there is no segmentation fault. Let me see what's stored inside of my heap, and I want to see it like we have our heap, and what I want to do now is look 10 bytes in one way and 10 bytes in the other way, or 10 integers actually in both ways. So we start our for loop with -10, then until I is equal or I is less than 10, and I just print the values of heap I. So now I'm accessing my 10 integers to the left, 10 integers to the right. I only have 3, but let's see what's stored there. Okay. Okay, this is what's stored here. Interesting. Maybe for that I can see where my middle point is. Let's use here 72. Then I know 72 is the middle point. Okay, so this one here is the middle point. This one are the values that are stored before my heap. This one here are the values that are stored after my heap. Or actually, we have allocated 3, so 1, 2, 3. This is my actually heap array. And we see that I can access here also the 10 because this is heap at position 10. This is heap at position 5, sorry. Heap at position 5, heap at position 6, and so on. So I can access that too. And I, again, have to go very, very far away. Let's see, 5,000. If that will create a segmentation fault. No, it will not. 50,000. Yeah, that will again create a segmentation fault. So what I wanted to show you here is that these are just the few code snippets we have seen. This work, yes, but obviously you should not access memory that do not belong to you, but it will work. So segmentation faults are not perfect. They do not show you exactly when you are off your array. They only occur when you are very, very far away. Most of the time they occur when you create or when you try to dereference null. But there's some kind of help to show you you are way too far away from where you should be. But if you don't have a segmentation fault, that does not mean you're doing everything correct. You still have to check your array borders because otherwise you can be way too far where you should be. Okay, second example for segmentation faults. This code produces a segmentation fault. Any ideas why? I will give you like 30 seconds, 1 minute. Let's see if you can spot it. It's not that obvious. Of course, you can also discuss with your neighbors if you spot something. It's a very, very usual problem people run into, and I still run into sometimes into that problem. Because it's, if you don't have a visualization, and obviously we have one, it's very hard to understand where the problem is. Did anybody have an idea? Yes. Yeah, you're on a very good track. So we do not return here the heap address. But let me argue, I hand over here a pointer and I write here the malloc inside this pointer. So that's call by reference. So technically it should work, right? Because I hand over the pointer. Yes. Let me show you how it works. You're correct, but it would also work without return. There are two possible solutions. One is return. I will come to that soon. The other one is the more advanced one, which will also work. But first, let's see what's the problem exactly. So we have our array here, which points to null. So if we are here, this arrow always shows the current state of the program. When we are here just creating our array, we have our stack and our heap, and we see here our variable array contains null. Null means it points to the memory location null. Okay, then we call our create array. So we are now here, and what happens now is we copy the value of the pointer, which is the address stored here, into my heap pointer. So we copy basically null into this heap pointer. So heap pointer now has the value null. Okay, looks good. Now what we are doing is we call malloc, allocate 3 times the size of integer. Yeah, this heap pointer points to null. We call malloc, so we get our heap memory. Still works. Yeah, looks good. We check for null here in our and do whatever we want. But as you can see here, my main array still points to null. We have here our heap pointer, which points to the correct address. And as soon as this create array is finished, the array in the main, so this array variable here still contains null. So the create array is over. We have lost here our variables. We still have our heap here, but we lost the connection to it. So when we want to access now our array at position 2, as you said correctly before, we are accessing the position 0 plus 2 in our memory. So really the memory location 0x2, which is again way too far where we belong to, and we get the segmentation fault. Okay, first solution, as you said, the easier one. Let's just return our heap pointer here. So our create array returns an int pointer. We create this, we return this heap pointer here, and it's stored into my array. So what happens is after the allocation of the memory, it returns the address of the heap, also here in the main, and this works. So we have now here, we can access array at position 2 because after the create array is over, we have the valid pointer here, and we can write something into this area here. That's the easy solution. The second one is the advanced solution, and sometimes you need that solution. And here you need to use pointers. Pointers, I think we discussed it 2 weeks ago. It's just a pointer to another pointer, so it contains an address, and when you go there, there's another address stored, and when you go there, then you come to the value. And what we need to do here is we do not hand over array, so the value of array which is null, but we hand over the address of array here. So the address of array is here, my stack address, let's say 0x7FED01. So when I create here then my create array function, I get a pointer. So the content here is the address of my function in the main. Then I have to dereference, when I call malloc, I have to, I get my, okay, let's go back to here. The heap pointer contains now the address of the array, but I get my heap pointer dereferenced, so creating or have a look at this variable here, go to this address, which is in the main, and store there the value or the address on the heap which contains my array. I know it's confusing, but it has the big advantage that we don't need return value here, because what we actually say here with this create array call is, I don't give you the address or null or whatever, but I will give you the location where you should store the address. So let's say this is my variable. You are the create array function. So I give you the variable. You allocate on the heap some memory, and then you give me the variable kind of back. No, you don't return it. That's a bad analogy. Let's try it once again. I don't give it to you. I just say, write there the address of the memory location on the heap. I still have that, and then I can have a look at it. That's basically what we do when we hand over the address of the array. And that's why we sometimes need pointers. And now this will work because we still, again, have access to my heap array. Any questions to this one?
Yeah, I just want to add it once again. As you said, that's a very, very common misconception, and we can observe this problem many times at the exams. So some exams we ask you to allocate something in another function, for example, and it's a very common misconception to just pass the pointer to the function, modify the value, so just writing an address to this pointer, but this modification does not affect the original pointer's value. So you're just modifying it in another function, but the original pointer, for this case here, it's the array pointer in the main function, is not affected by writing another address, another value to the pointer in another function. So it's very important also for the exams to understand this.
Yeah. Okay, if there are no questions about that, let's continue that. Until now we allocated memory, but we never used it actually. We just wanted to, we want to have memory, but now we want to also use the memory. There are a few possibilities.
Yeah, there are a couple of functions. We will talk about 3 of these functions today. They are all in the string header file. So you just have to include a string header file, and then you can use these 3 functions. The first one we are talking about is the function called memset. We're passing a destination pointer, the value c, and a number of bytes, so the first n bytes in this case, that will be set to this value for a specific pointer. So we pass a pointer, we want to store the value c, so can be an integer value, and we just write this value into the first n bytes of our memory that we pass as a pointer. So the pointer is addressing this memory. Quite useful in some cases, for example, if we want to initialize some memory with zeros, for example. I mean, we could use realloc, but in some cases you want to, for example, erase and clean all the memory that you have. And for this, you could, for example, use memset, because then you know the memory is in a predictable state and you can just use it. Another function we would like to mention is the memcopy function. So you're copying n bytes. So again, there's one argument for the number of bytes. But instead of just writing a value, as we had it in the memset function, you're writing from a source memory area to a destination area. So you're really copying the bytes from a source, can be any memory location, into a destination memory area. So it's really just a copy of the bytes from one area into another memory area.
And we already saw a function pretty similar than memcopy. Any ideas what that is? Also in the string.h library. Yes?
Yeah.
String copy, yeah. So
Exactly.
memcopy is basically the same as str_n copy, where you can also hand over the number of elements, but with one addition. I've Googled it before. Str copy copies until, so str_n copy copies n bytes, or it finds the null byte. So if the null byte is earlier, then it only copies until then. Memcopy copies always the n bytes. So again, you can say, I want to have 100 bytes copied from here to there, and it works like that. Yeah, no matter what's the content.
Yeah, we could imagine it's an image that we store somewhere in the memory, and we then can really, or we know it's 200 bytes long, whatever number, and we can copy the whole image from one memory area to another one. So yeah, but it's quite similar to string copy. And there's another function, again, quite similar to somewhat that we have seen already. It's the function called memCompare. And again, we have 2 pointers and a size. So how many bytes should be compared between these 2 memory areas? So we compare n bytes from memory area 1 with memory area 2. So these are quite useful functions.
Yeah.
They're already quite similar to something that we have used already. But for example, especially memset can be very helpful to just clean the memory area, and that okay, I'm sure that is zeroed, so all the bytes in my memory area are 0, and I know there is nothing that could surprise us when we use it.
Yeah, I think we are at the point where we now try to break our computer once more.
Yeah, that's right. Because now we want to allocate some memory.
Yeah, the question is how much memory can we allocate now? So I have written this small program here, which basically has just one constant, very large, which when you have the translation here, in the end, it's 1 gigabyte. So 1000 times 1024 times 1024. In the end, we result in 1 gigabyte. And what we do here is we call malloc. Again, I skip the null check here. Of course, you always should do the null check. But for this, it's okay. We also lose the memory, to be honest. We do not free it. Yeah, it's fine. Trust me, for this educational purpose. But we call malloc with a very high number of bytes. So each call in this for loop is 1 gigabyte. And we do this now 20 times. So my computer is not the best one. It has 16 gigabyte RAM.
Oh.
So when I do that with 20 times, I allocate 20 gigabytes. Let's see what happens.
So we have a backup laptop here if your computer will crash, so don't worry.
Realloc. Okay, it gives me a warning because it's set but a variable set but not used. That's fine for me now. And I want to. Okay, the output is it started with 1 gigabyte, 2 gigabyte, 3 gigabyte, and so on. So I always print here just the number of gigabyte we have reserved, and 16 gigabyte allocated, 17, 18, 19.
Maybe there's some hidden memory in your laptop?
Let's try to break it really. Let's say I want to do like 4000 gigabyte. Compile it again, run it again. wow, I have more gigabyte than expected.
That's cool.
It would be cool, but unfortunately, malloc tricks us again a bit. So yes, we get the memory theoretically, but it really belongs to us only when we use it. And I will not demonstrate that now, but I can show you here. So what I've done here, this is for a 32 gigabyte RAM allocation, and this works. Also here for the 40,000, it works. Why is this the case? Yeah.
But yeah.
When we do it like this, so when we call memset after malloc, which means we actually use the memory, then we get into troubles because malloc gives us the promise that we have memory, but as soon as we use it, kind of malloc says, oh, you really use the memory? No, then I don't have that much for you. So as soon as I really use the memory, then I get into troubles. And then in this case, I set everything to 1 here. So then my computer will crash. Have you ever tried it?
No.
I think so. What you could do is try it in a virtual machine. What should happen? Virtual machine crashes. Yeah, okay, you can restart it. But that's a problem you should not do. Yeah, that's something you should not try on your program, especially if deadline is approaching. But what I wanted to show you is, so malloc works also with whatever you want. But as soon as you really use the memory, then malloc says, okay, I don't have that much memory. You can only use the memory you have, or you have available. We have available here.
So once we are writing into the memory, we are really limited to the physical memory that we have.
Any questions to this? Yes. Yeah, it's a good idea. So when we do not use it, we don't know. It's just a number. Yeah, we can have arbitrary much memory. Yeah. The question is, if you do not write to it and allocate it, it frees up. So I think if you call Valgrind, of course, you will see that there are memory leaks. Yeah, of course. But you really get the memory only if you write to it. But as a programming perspective, I think you don't really care about that because there are memory leaks anyway. And in most cases, you use your memory and just don't want to allocate, I don't know, gigabytes and never use it. That's also what you should not do, allocate memory and never use it. So, but yeah, theoretically, malloc, or if you have that allocation, no matter what size, Valgrind will see it, that you allocated memory. But one thing to add here, maybe we shouldn't say it, but one thing to add, it's not that a big problem if you do not free the memory, as we have seen here, because at the end of a program, the operating system sees that you have memory to free and frees it for you. Yeah. So that's why programs don't crash. But here in ISP, we want you to learn programming in a way that you clean up your own mess. So if you allocate something, you always have to free it on your own. Okay, let's continue with maybe the most important topic for today, there is one more function we want to show you. We've seen calloc, we have seen malloc, and we've seen free. One more called realloc. And when should we use realloc? In the case that, let's say we have here an fgets, we read 100 characters, that works, but we want an arbitrary long user input. So that's also what we say is one of the use cases for the heap. We don't know how much memory to allocate with malloc either. So when we call malloc, we have to specify the number of bytes. And sometimes we don't know how much memory I need. And then I need realloc. So realloc allocates more or also less memory to an existing heap pointer. Yeah. So previously you have malloced or calloced, and now you see, I need more memory because user is typing and typing and there is no end. So I need to make my heap array bigger, and realloc does that for us. So it takes a pointer to an existing heap array, and the second argument is the size of the new size. Let's say when I have an array of 3, I hand over 5, and then I have an array of 5 elements on the heap. The content will be unchanged. If the newer size is larger than the older size, the added memory will not be initialized, so I don't know what's in there. Very important, if it's not possible to make my memory block bigger because there is another memory block very, very close to it, then realloc finds a new location for our memory block and stores it there.
At least it tries to find.
It tries, yeah, if there is one, yeah. And it returns the segment of the memory block where the new location, basically. Okay, so how to use realloc? Let's say again we have here our malloc array with 3 times size of integers, so we are creating 3 times 4 bytes, store that in the grades pointer, which is basically an array of 3 times integer, check here if malloc works or not, and then I store here 3 values, 1, 2, 3. So when I'm here, the memory allocation, let's say the memory allocation works, then I can store 1, 2, 3 here, and on the heap in my memory, the values are there. Now, Sebastian came to me and said, okay, we have 2 more students. We need 2 more memory locations to store the grades. So we need more memory for that. We don't know what's in there here, so we need to be sure that enlarge our current array, and we call a realloc. First argument is the existing pointer to the existing array. Second argument is the new size, so I want to have 5 times size of int. So from 3 go to 5. When this is executed here, it looks if it works. In this case, it works because there is no other memory allocated directly after this grades array here. So we again check if grades is null, that works, and also grades at position 3 and grades at position 4 can be written here with 4 and 5. And then I have a 3, which then just frees my memory on the heap. So far, so good. That's the most basic case of a realloc. What if this memory cannot be made bigger? So let's say we have our grades array here, and somewhere else on my program, I've also allocated 1 integer and stored there 72. As we know, it can be anywhere in my program because it's a heap, it's just not ordered. So let's say I cannot make my grades array bigger here, but I call realloc because I want to make it bigger. What happens now is realloc here, when this is executed, just finds another place on the heap where I can store my values. So it sees, okay, this does not work here because there is another segment here, but here below is enough space. So it copies the value 1, 2, 3, and it has additional now the possibility to additional 2 grades here. But the thing is that my grades pointer, which is stored here on the stack, still points to the old memory location. Because when we remember what we said, what realloc returns the new memory location where the data is stored. It might be the same that before, but it could also be that's another memory location because we had to move it somewhere else on the heap. So what we need to do here is we always need to catch the return value of realloc, and then we don't lose the information because it's stored somewhere else. And it's very, very good practice to store that in a temporary pointer, in a temporary variable. So I create here another variable on my stack which points to the new memory location. The old one still points to the old location here. I check if that works, because if this realloc would not work, I get again null here. I have to check if temp is null. And if this works, then I set my grades, so my original pointer, to the value of temp, which means now also grades points to the correct addresses here. And again, I can now write here values inside. And then, of course, I can free it if I don't need to use it anymore.
And yeah, we will see it on the next slides, but I want to highlight it once more. So the grades pointer that is passed to realloc remains unchanged. So this is the same pointer, it points to the same address on the heap, so before the realloc call and after the realloc call.
So this grades here still points to the old location, so we have to manually reset it to the new location, but we have to store somewhere the new location, which is this temporary pointer. And as soon as we know that it worked, because there was memory available from realloc, then we set it to the temporary location, and now we have these grades again at the true location. That's nearly finished. Yeah, we have one more thing to add here. There's one more problem, because if realloc fails, this grades array is still allocated. Because when we go back here, this grades points to this one here, but if this temp does not work, so if this realloc does not work, it cannot find memory location, but it does not free the old memory location. So we have to manually free our grades in this case, because otherwise we have again memory leaks. You will see that next week in the practicals. It's I think they called it a memory management guide, where you see in detail what you have to consider when you use the heap. You have to use the heap for assignment 3. And there are a few things to consider. I think I also have it in a few pages, so like a summary, what you have to consider. But very important is the temp pointer. And if the temp pointer is null, so it means we have no more memory, we have to free all the memory allocated, which is also, in this case, the grades array allocated before. Okay, I have a question now for you again. So everything we saw now about malloc and realloc, this is a code snippet, and there are a few statements about this code, and you have to decide now which statements are correct. So in the first few lines, we are creating an array with 2 times a float. So we want to store temperatures here. Yeah. We check the temperatures if it's null, so if it worked. If it works, we store 1 and 2 into the 0th and 1st element. Then we want to call realloc. Store it in the temporary variable, check for that, free the temperatures as we've seen before. And we want to store one more value.
Okay, maybe 10 more seconds.
Yeah. Okay, let's see. Yeah, very good. So let's go through it. In line 7, we allocate 8 bytes on the heap. Yes, we are allocating 2 times size of float, which is 4. So 2 times 4 is 8. That works. That's correct. This code writes to memory that does not belong to the program. Yes. Here in line 19, there are 2 issues. So the first one is we don't have this array anymore because it might be moved to another location in the temp variable here. So we are accessing here the old pointer and the old array. It could be that the array is still there, but we don't know. It could also be moved. And one more thing, we don't make the array bigger. We say it's the same size, 2 times size of float. So that's also a problem, and we cannot, when I have just 2 elements, the index 3 is too much, so I'm off by 2 in this case. If there is no more memory, we end the program correctly. Yes, that works, because if here is no more memory, it works. And if here is no more memory, we free the old one, so that's also correct. And the last one, we enlarge the temperatures array by 8 bytes using realloc. It's wrong because it's 2 times 4. It's the same size as before. This here, the second argument, is not the bytes. I want to make it bigger. It's just the new size. And in this case, this realloc is really useless. Okay. Can the size of the array also be made smaller? So yes, of course we can. So let's say we have same problem as before, malloc with 3 times size of integer. We call realloc with 2 times size of integer. So obviously I make it smaller. What happens? it's still, the value is still here, but my array is officially only 2 integers big here. So as I said, this value of grades at position 2 will not be deleted. It's still there, but we cannot be sure because, yeah, it could be overwritten in the meantime. So I should not use it anymore. Okay, so the summary for today. Realloc like this. Yeah, call realloc with the new size and the pointer. Store the return value of realloc in a temporary variable. Then check if this temporary variable is null. If it is null, free the original pointer. And if realloc worked, so this null check does not fire here, we set then the original pointer to this temporary variable.
Yeah, if we don't follow this guide here, these steps, we might lose the access to the memory area on the heap. We might lose the original pointer. We could also lose the new pointer if we don't store it in a temp variable. And of course, we also have to take care of freeing the memory properly. So if it returns null, we have to free it, but also, as usual, at the end of the program, we should free it or when we don't need it anymore.
Okay, the last 5 minutes I want to spend on like of a first idea for the next lecture, where we talk about data structures. We have seen structs a few weeks ago, and structs are now becoming more and more important because, as you might can guess it, we not only want to store integers and floats on the heap, but maybe structs or combinations of different data types. So let's say we have here our student. Student is a struct with a name and a grade. And I have here my student Michi, and I can create this student with this create student function. So I call here inside malloc. But with the size of a student, so size of student means it's the sum of all individual elements inside of the struct. In this case, it's 28 plus 4, so it's 32. So size, so I get here 32 bytes allocated, and I can store it into a student pointer. Now something new, I think. But it will be very important in the next lecture. I want to, of course, edit the grade because the grade should be free and the name should also be set here for this new student I created on the heap. So what I need to do is I need to dereference my student to get to the value of the student and then dot grade to get to the actual attribute. So before, when it was not a pointer, I can just write this dot grade to access the grade of a student. But in this case, it's a pointer, so I had to dereference it first, and then I can access the member of it. Similar, in this case, when we use struct copy to copy this Michi name into my struct. This one is the name here. I get handed over. And this one is the destination. And it's again, it's the dereferenced student dot name to access the member. This is a very, very ugly way to write it. And there is luckily another solution or another way to write it. So pointers must be dereferenced to get to the content before we are accessing the member. And the better notation is to using the so-called arrow operator. And this arrow operator, which is basically like this, does the same as this one here. So what this arrow operator does is it dereferences student and access then the member of it. So it's way faster to write it like this than using the parentheses, then the asterisk, and then the dot. And it's the same, and we will from now on also use this notation here. The only difference is between the dot and the arrow. The arrow means that the student is a pointer and you have to dereference it before. You will get used to that. In the beginning, it's a bit, complicated to understand, but you will get used to it. What's the difference?
So yeah, the code definitely looks more beautiful like this if we use the arrow operator. So we don't have to dereference it anymore. We can just use the arrow to access our members of the struct. But in this code snippet, there are some parts missing. As always, when we use malloc, we have to do something. We have to check if there is an error. So we have to check if the returned pointer is null. Of course, we also have to do that when we want to allocate structs in the heap. But we don't only have to do it in the create student function. We, of course, should also do this in our main function, because we want to end our program properly if there is an error. And we cannot only create one student, but we could create multiple, so an array of students.
So in this case, we have just created Michi. Now let's also create Julia and Tanya. Let's say our create student is the same as before. Limited space here on the slides. But what you have to do again is, if this create student returns null because there is no more memory available, you have to always check if it worked. And if it has not worked, then you have to return the program. There is again one error here. And I think for the sake of time, let's resolve it directly. If Julia here is null, Michi is still available because Michi is still on the heap. So what we have to do here is we have to free Michi when Julia is null. So every previously allocated memory has to be freed before ending the program. If Tanya is null, we have to free Michi and Julia because they are both still allocated on the memory. And that can be very, very confusing and a lot to do. So what we could do is to store the students in an array. Let's say we have here our array. Let's say we have here our checks again for the students. That was fast. I thought there's one more. I thought there's one more slide, but as I said before, we can store that in an array, and this is very important for the next lecture. This is now a student array, so an array of free students of student pointers, because they are pointers to the heap.
But that's it, basically. We will talk about it more next time, so in 2 weeks, when we talk about data structures. But I think for today, that's all we have. And thanks for being here.
Thanks for being here.
See you next week or
in 2 weeks. In 2 weeks with the lecture. Thank you.